Why is the screen one? I don't know what's happening. I'm going to try a different.
I'm also
Really?
well.
Granted, there are really only 5 levels.
Yeah, I mean, yeah, you were like, go through 6 months.
Those are good. I don't know why.
Okay.
Yeah, so why?
There's a lot of things. That's sad.
Just like, yeah, it's more.
I don't know why those.
Okay.
Reading.
What's that?
Oh, no, read it. Never.
I don't know. I think the USB is making the computer crash. Okay. Sorry about this. I don't know. We wasted 7 minutes already. Well, happy Friday. At least it's Friday, right?
Yeah.
Yay. Okay, so let's do some recap questions. What is supercritical fluid chromatography? Why is it called supercritical? Yeah, go ahead. Say that again. Yes, so carbon dioxide at higher than ambient temperature and pressure becomes a liquid, and that is why it's called supercritical fluid. All right, what is reverse phase chromatography? When I say this, meaning what would be your mobile phase? What would be your stationary phase? Go ahead, Mitch. Yes, the mobile phase is a polar compound and stationary is non-polar. And then your compounds are interacting with the stationary phase via non-polar interaction. And then after you start with the polar phase, in order to let the non-polar compounds leave the column, what do? So they're interacting with your stationary phase. And then there's water or very polar compound going in the mobile phase. What do you do to let some of those interacting leave the stationary? Or weaken the interaction of the stationary phase so that they leave and you guys can go home and it's not a whole analytical
Gradient?
do gradient. So I would increase the strength of the mobile phase by making it less polar. So I would increase the concentration, say, of acetonitrile or methanol, make it less polar so that the compounds interacting with the column or the stationary phase starts leaving or move faster. Okay. So in reverse phase, what would be the compound that travels the most? Most polar or most non-polar? Go ahead, Raz. Most polar, because you start with water or a polar solvent, then the most polar will keep moving faster with your mobile phase. Very good. What does TLC stand for? Wrong. Another answer? Yes, absolutely. Absolutely. Yeah, thin layer chroma both gets +2, even the one that answered wrong. No, just kidding. Okay, how does TLC differ from paper chromatography? There is no tender love and care in paper chromatography.
You can choose what the stationary or the beyond the stationary phase, what the solid structure of it is. You can choose from silica or alumina or cellulose instead of just having paper made of cellulose over time.
That's one, but what else? Yes. Higher resolution, because you can choose that say silica fine particles are uniform, so you get better separation and better reproducibility each time you analyze. Okay. So what is the difference between isocratic and gradient? Meaning, what is isocratic elution? Gray.
Right, where you just stay at the rate,
Rate and what else? Same concentration.
and grading. Increasing whatever period.
Exactly. So isocratic by the name, nothing changes with the mobile phase. Same concentration, same rate, same temperature, same everything throughout the run. Whereas gradient elution, you're changing something, and mostly it's the concentration of your mobile phase. You're making it stronger to elute, to get your compounds that interact with stationary phase leave the compound. And that explains what increasing the strength of the mobile phase. Depending on your starting mobile phase, if your mobile phase is polar, over time you decrease polarity, that's increasing the strength. If your starting mobile phase is nonpolar, like 100% acetonitrile or methanol, over time you add water, you make it more polar. Okay, so changing your mobile phase over time is increasing the strength. It's not in one direction. It's not always increasing polarity or decreasing polarity. Sometimes you're increasing salts. Sometimes you are changing the composition, adding a ligand to your mobile phase. So changing the mobile phase, meaning increasing its strength over time so that you can get your solutes or components to move faster and shorten your analytical time. Okay. So last time we were talking about partition chromatography, and we said we stopped at this here, hydrophilic, which is a form of partition chromatography. So it is liquid-liquid, and it is a form of normal phase as well. So it is partition chromatography, and it is a type of normal phase, meaning in normal phase, you have, in normal phase, just that you remember. So you have polar stationary phase, and then you have nonpolar, at least at the beginning, nonpolar mobile. And normally, your nonpolar mobile phase does not mix with water, immiscible with water, okay? So that is in normal, regular normal phase. Helic or hydrophilic interaction chromatography, you refer to it as helic. Your non-mobile phase, okay, and your mobile phase is a solvent that can mix with water, so miscible with water, like acetonitrile, methanol, but not hexane. It can mix with water. That's the difference in mobile phase. In normal phase, it is immiscible with water. In helic, it's miscible with water. So these are key differences. Silica usually is your stationary phase that is bonded with a polar functional group. Okay, so that would make it polar stationary phase in both regular, normal, and helic the same. And mobile phase is different, either immiscible in normal phase or miscible with water in hydrophilic. Now, why is this sometimes really important. Helic is applied when you're working with compounds that are, wait a second, this is in the middle of the. So here you're working with compounds that have limited solubility in water. So if you have, instead of reverse phase, you have compounds that are not soluble in water. I need to not confuse you. So reverse phase, your stationary phase is nonpolar, like C18, for example, a chain of 18 carbons, nonpolar. And then your mobile phase is mostly high concentration of water. 100% or let's say 99% water. This is how you start. If you're running reverse phase, your solutes must be soluble in water. Why? Soluble in water. Why would the solute must be soluble in water? If you're running reverse phase, go ahead, I'll get there. Go ahead. Yeah.
Because your mobile phase is water, so if it's not dissolving in the water, then it can't actually go through and interact with the station.
Exactly. So it's not soluble in water, so that won't work. So reverse phase won't work. So then we will go to helic. Another that is a polar component that does not, or polar components that don't retain adequately on the nonpolar stationary phase. So also in reverse phase, you need to have nonpolar interactions, but if you don't have this interaction, it doesn't happen. That is in the polar components that does not retain adequately on the, yeah, exactly. So if you have nonpolar and you have polar compounds soluble in water, but they don't interact with your stationary phase. So we have to try something else. And in this, and instead of helic, well, we use helic, sorry, instead of normal phase, because sometimes we need to have a detector like MS, and immiscible solvents with water don't go well with mass spec. So that's when helic plays a role. So it can replace reverse phase when your solutes are not soluble in water or when they don't have good interaction with your column. It replaces normal phase when you need to add mass spec and you need that miscible with water solvent that is less viscous. Okay, so that's when helic plays a good role. It's kind of like the balance, and it replaces both normal phase and reverse phase. So that's when we use helic, okay? And it's commonly used to analyze small molecular weight compounds. It's very good for amino acids, di and tripeptides, phospholipids, polar lipids, and organic acids, sometimes also polar lipids like monoacylglycerols and diacylglycerols could be analyzed by helic. I made few edits and I put the corrected slides on Canvas.
So can you say small? What is there a definition of small, like, is it-
Yeah, so small, like I would say, ranging from, let's say, 125 molecular weight gram per mole, potentially up to 1 kilodalton, which is 1,000 grams per mole. That's kind of like the typical range. Good question. Any other question? All right. So in HELIC, hydrophobic interaction chromatography, interactions between your solute and stationary phase are mostly There's one of them, van der Waals, and electrostatic, which is ionic interaction. Not hydrophobic, and obviously no covalent bonding in any chromatography is what you want. All right, so hydrophilic interactions based on polar interactions, that is going to be electrostatic, hydrogen bonding, or van der Waals. Electrostatic or ionic is the same thing.
With this hydrophilic interaction, is the silica pre-wet with water again, or some other solvent?
Well, it's a partition chromatography, right? So that whatever you put in there would be liquid, aqueous liquid.
Okay.
Yeah.
Because I have also the idea of silica as the liquid bonded to the surface.
Yeah, so it is in some form a liquid that is covalently linked to silica functional groups. So it's wetted. Yeah, it is liquid. Now, there is hydrophobic interaction chromatography, and we refer to it as HIC. Okay, so why is Brittany texting? Did she post the assignment? Huh? It is posted. So there was a question that assignment for pre-lab quiz was not posted on Canvas. Is it posted? Can you see it? Okay, it is there. All right. HIC then, so here you have, instead of hydrophilic interactions, you have hydrophobic interactions. And this is a form of adsorption chromatography. Now, this is not partition. So your stationary phase is solid, and you have weak interaction with the stationary phase. And what we use is a mobile phase that is high in salt. And this is mostly a chromatography for proteins. The most applications are proteins. It could be large molecules, mostly proteins. Some of them can be antibodies. Antibodies are proteins too, made up of protein polymers. So this is very common for protein chromatography or chromatographic separation. Stationary phase is a hydrophilic support, but you have a bonded ligand that is hydrophobic. The butyl saccharose is a very common stationary phase we use in HIC. Mobile phase always is a high concentrated salt solution that you start as 1 molar, and the way you increase strength over time is decreasing salt concentration. So let me demonstrate or visualize, help you see the process by visualizing what happens. Proteins have charge on the surface, right? This is common knowledge of protein. So they carry charge. In order for them to interact with your stationary phase, we add salt. What does salt do to the protein surface? Some of you might know this. When you add salt, what happens to the charge on the protein surface?
It shields them and
Yeah, shield them, neutralize them, right? So if you add ammonium sulfate, which is made up of So this is plus and this is minus. So when you have charges on the protein, some are positive charge, some are negative charge. So the constituents of the salt interact with the charges on the surface of the protein, shielding the charge. And proteins on the surface have hydrophobic groups. When you shield those charges, then the hydrophobic groups can now interact. I hid from Wednesday. So the hydrophobic groups now can interact via weak interactions with the hydrophobic surface of your stationary phase. So this is with high salt. Now, after they interact, you want them to leave the cone. So you decrease salt concentration. So you start with 1 molar, then you go down to, let's say, 0.75, 0.5, 0.25 to 0 molar salt. So you build gradients if you want to separate proteins. If you don't want to separate protein, you just want to get all the protein and separate them from carbohydrate, let's say, you just go from 1 molar to 0. Don't have to separate anything. You collect the protein right away. When you go down to 0 concentration or 0 molar salt, then now you're back to having charges that they will not interact with your hydrophobic stationary phase. And the another thing that you can see here in the picture, the most hydrophobic protein on the surface will interact the most, get retained the most, and the least hydrophobic will interact less and will elute first. Okay, so because it's hydrophobic interaction, the most hydrophobic will interact the most, and the least hydrophobic will interact the least. So the first protein leaving the column would be the least hydrophobic. Any questions there? Okay. So in HIC, interactions are mostly what? It is a trick question. The answer is in the question. Yes, Razzie. Hydrophobic, yes. You know, I know it's Friday and you're ready to go home and everything. Now, because you're ready to go home, I'm going to stimulate your thinking and talk about a more complex form of chromatography, which is ion exchange. Students love it, not. They don't love it. All right. So, ion exchange. What does it mean when you hear ion exchange? Can you simplify it to me? What does ion exchange mean? What, Violet?
It's like the equalization of charges between like a barrier.
Okay, think about it from what does chromatography do? What's the definition of chromatography?
Separates.
Separation. So in ion exchange, what's happened?
It's separating the charges.
Separating compounds that carry charge. And they are exchanging between the stationary phase and the mobile. Okay, so ion exchange, you are separating ions. You are separating molecules that carry charge. They can be small molecules or they can be larger molecules, but molecules that carry charge can be separated by ion exchange. Now let's complicate it a little bit more. You don't want me to complicate? Why?
Less complication is good. Why does it have to be so complicated?
I didn't create chromatography. I just teach it. Okay, so you have cation, anion. Notice you have ion exchange. Okay. Cation, ion anion exchange. Now tell me what that means. What is cation exchange? Yes, go ahead, Razi.
Cation's a positive, it's a positively charged ion, so if it's exchanging, it's transferring to someone else.
Or transferring between the mobile phase and the stationary phase. In chromatography, we have stationary phase and mobile phase, so we are exchanging positively charged ions. So exchanging, separating, exchanging, separating positive ions. All right, this one. Yes. So exchanging, separating negative ions or molecules that carry negative charge. All right. So in order for these kinds of ions, positive and negative, or positive or negative, let's talk about the positive, okay? If I want to separate positive ions or molecules that carry positive charge, my stationary phase in a column should carry what charge?
Negative charge.
Yes. Negative. Negative. Very good. That's what I want you to remember, because that's where students get confused. When I say cation exchange, and in an exam, I tell you, what is the charge on the stationary phase? What do some students say? Positive. Which is wrong. Snake. So you're exchanging positive ions. You're separating positive ions. So your stationary phase is negative. So the naming follows what you're separating, not what's on your card. Okay, so I'm trying to simplify on a Friday afternoon. Who's with me? Yay. Very good. Very good. All right. So the way we set up is we have a stationary phase or a resin that is cross-linked polyelectrolytes, meaning polymers that carry charge. Okay, so we have two types, highly cross-linked. So you have a lot of cross-linking, then the pores are small. When you have cross-linking, then the pores are really, really small. That means for small molecules, separating of charged small molecules, like amino acids can be charged and small. Okay. Whereas lightly crossed, that means they are cross-linked, but the pore size are large. This is for large molecules, like proteins, for example. So large molecules, lightly cross-linked, highly cross-linked for small, lightly cross-linked for large molecules. And then now you would have a functional group on that polymer, so polyelectrolytes, either negatively charged, O minus here, and then you have your cation, a molecule that is positively charged and displaces a sodium ion and interact with your stationary phase. And if you have anion, you would have a functional group that is positively charged. And then you have a salt like chloride, for example, that displaces that molecule, or the molecule displaces the salt to interact with that positively charged. So either negatively charged or positively charged with a salt ion. Okay. So polystyrene is a common polymer. And then here you have your R is derivatized to be either positively charged, so you have anion exchange, or negatively charged, you have cation exchange. A very common resin is polysaccharides. So you have cross-linked polysaccharides. The OH is the functional group that get derivatized into either a weak acid, a weak base. So weak acid, we have negative charge. So this is anion or cation exchange. Let's see if you were with me a moment ago. Cation exchange, thank you. And then here we have weak base, so it's positively charged. So this is an anion exchange. And then you have a strong base or a strong acid. And I'll tell you the difference. When do we use a weak acid or a weak base? And when do we use a stationary phase that has a weak base, a strong base or a strong acid? Okay. So molecules, yes.
Wait, can we go back for a minute?
Yeah, absolutely.
So the squiggly lines, are you saying that's the stationary?
This one
No, down on by where it says,
here.
like, are these,
Yeah, these stationary phase, like a polymer.
okay,
And you have the OH group on like glucose subunits. They are derivatized. Yeah, so this is like here. So the O is derivatized and this whole polymer is behind that squiggly line. So usually your stationary phase has multiple OH groups and each one of them is polymerized or derivatized to carry a charge.
so the polysaccharide base and the polystyrene, use those as for stationary.
Yeah, so these are the ones that kind of are your resin that you fill the column with. And then they have functional groups like here, OH groups that get derivatized to carry a charge. Yeah.
So does it mean that for proteins or amino acid group, which are already carry charges, you don't need to derivatize?
No, these are just your stationary phase, right? So the stationary phase needs to be derivatized and ready to separate the charged molecules. Yes. So these are on the stationary phase. Okay. And then your molecules that you want to separate, you use this stationary phase to separate them. Good. Yes. Yes.
What about your mobile phase?
Ah, we haven't gotten there yet. The mobile phase usually is a buffer in this case.
And then I just want to make sure the difference between using the polystyrene or non-polar.
Polystyrene or polysaccharides.
So using the polystyrene would preferentially hold on to more polar things.
No, don't worry about polar, non-polar. It's just the type of resin.
And it
So
doesn't play.
no, it's a polymer, right? It's a polymer that can be derivatized to carry a functional group that is charged.
But otherwise it doesn't really matter.
No, it
What it
doesn't
is.
matter because it's not, and nothing is interacting with your molecules other than the charged groups that you're putting on that resin. All right, what a Friday. Okay, so you can choose your stationary phase based on the selectivity that you want. Selectivity meaning what molecules you want to separate and how much resolution you want to get, okay? So you need to understand your molecules, their charge. When we talk about charge, it's not only plus or minus. You have to remember something of your chemistry, ionic valence. So what is the charge in that outer energy level or shell? So the valence and then the radius and how much concentration. Okay, so let's say you have a molecule that carries 3 positive charges and a molecule that carries 2 positive charges and a molecule that carries 1 positive charge. Okay, so this one has higher charge density, more charges. This is going to be retained more on your column. There's more places that it's going to interact with your stationary phase. And the one that has the least ion charge load, it will interact the least and will elute first. That will be first, second, third order of elution. Okay. So that's the characteristics of the molecule is important. Also, what is important is how closely your molecule are to each other in their characteristics. Do we have them being either positive or no charge, and I just want the positive ones? Or are they positive and negative, and I just want to separate them from each other? Or I have multiple molecules that are all positively charged, and I want to separate. Okay, so that is how I would choose strongly acidic, strongly basic, or weak cation or weak anion. So if I just want to separate positive from negative and collect all the positive, collect all the negative, or the charged from uncharged, then I really don't care about having weak. I just pick strong acidic or strong basic and do isocratic elution and separate them. The strong acidic and strong basics, they are not impacted by the pH. Your mobile phase is a buffer. So usually the way we change the characteristic of the buffer is changing the pH or salt content. So if you have a strong anion or strong cation exchanger, no matter how change your pH, it won't impact the interaction of the compound, won't change anything. So these are used if you're just doing, like I said, separating charged from non-charged molecules or positive from negatively charged molecules. But oftentimes this is not. You have closely related molecules like proteins, closely related in the charge they carry at a particular pH, then you need to choose either weak cation or weak anion. Why? Because then you can change the pH of your mobile phase and help with the separation and the of your components. So you choose your stationary phase based on the purpose. Now, when we cover HPLC, I'll give you examples of situations where you have to choose. So all I want you to know right now is strong acid or strong base, no matter how you change the pH, you won't be able to change the ionization state. If you have weak cation or weak anion, they're impacted by the pH. All right. So the composition and the pH of the mobile phase is what you need to worry about when you're doing gradient dilution. Change the pH or change the ionic strength. You will change how the molecules are interacting. Okay, so if you have a positively charged molecule, okay, and then you increase the pH, what happens to the positively charged molecules? They lose their positive charge, right? So when you increase the pH, the positively charged molecule will interact less with your stationary phase. That's just an example of when you change the pH, what happens. Okay. Questions? Or you just want to move on? I'll keep giving you examples in the next few lectures. Yes, Rachel. Yeah, let's say I am let's say proteins have NH plus, right? NH amine groups. Okay, so you have amine groups on the protein. So if I change the pH of the mobile phase by increasing the pH, I'll have more OH minuses, right? So I will lose protons from the surface of the protein. Then I lose the positive charge, then I lose the interaction. I weaken the interaction of the column, then they go. That's how pH. Salt, how does salt work? If you add NaCl, what is that going to do? Then dissociate, like that, huh? So your Cl minus is going to interact here, and the Na plus is going to displace and interact with your stationary phase, so you weaken the interactions. So increasing salt concentration weakens the interaction.
What are some typical salt concentrations you use?
Oh, typical. There's no typical, because it depends on the molecules that you have in that charge load. So sometimes, oftentimes, it's anywhere between 0.05 molar to 1 molar. Yeah, so it's really a range depending on what you are working with.
Sorry,
Yeah,
what was the word you said with the sodium interacting with the column?
displaces. Yeah, it displaces your molecule and just takes its place. Displaces, takes its place on the column. Yeah,
If you were doing it the other way around, it would be chlorine interacting.
it's not, it's happening simultaneously. So your chlorine is, Cl minus is interacting with the
Yeah,
positive.
but I'm saying that like if you had,
A negative,
Yeah.
yes, then your Cl minus is displacing if you have anion exchange. Even I have to think about it.
Would you say that all these alterations of the salt and the acid, would that be called, strengthening the mobility?
Increasing the strength of the mobile field. Yes, anytime you change the mobile composition, you are increasing the strength so that you shorten analysis time and get the molecules off.
Things like proteins, is it easy to go too strong? Increase the strength too much?
So protein is the hardest molecules that you can ever work with.
That's all I wanted to make.
I just because they vary so much and they carry a lot of different charge, not only one type of charge. They have a combination of charge, positive and negative. You go with the net charge and the pH changes that, the salt changes that, right? My students love working with proteins. Look at Saj. Yeah. Okay, so what's the answer here? Yes, I like this. Yeah, you're paying attention a little bit. Okay. All right. Well, happy Friday. Have a great weekend. I'll see you on Monday.